Okay, so we're going to have our second speaker of today, Fay Dowker. Yes, we need a pointer. Let's plug the USB here. Let's see if it works. Okay, yeah, perfect. So Fay is going to tell us about what aspects of GR will be recovered from quantum gravity. Please.
Okay. Thank you very much to the organizers for this great meeting and for inviting me to speak. So I hope that my talk is going to focus on causal set quantum gravity, which is the approach to quantum gravity that I work on. But I hope that it will illustrate some rather general questions which arise, I believe, in many, if not all, approaches to the problem. So you can take this as an example theory which illustrates some of the questions that I think are go across approaches. So in the spirit of this meeting, I hope that it will be interesting to everyone. So what do I mean by what aspects of GR will be recovered? So first of all, I'm assuming that one aim of every quantum gravity approach is to recover general relativity as an approximation in certain circumstances and at large scales. So in the same spirit as recovering classical mechanics from quantum mechanics, recovering fluid mechanics from molecular mechanics. So that may be controversial, but I'm just going to assume that that is a goal that across quantum gravity approaches. So what do I mean by what aspects of general relativity? Well, there are certain things which are up for grabs in GR. So what kind of spacetimes are part of GR proper or physical GR? So for example, do we allow solutions of the Einstein equations in which there are closed timelike curves, for example, closed causal curves, closed causal loops? Do we allow, or do we allow only, do we make the most restrictive causality condition we can put, which is that spacetime has to be globally hyperbolic? We don't know. Those are all formal axioms that one could apply to general relativity. And in my view, it's part of the job of quantum gravity to explain or predict exactly what those conditions for the emergent theory of general relativity are. So here's a rough plan of my talk. I'm going to talk about the gravitational path integral in general, and I'm lucky because I'm speaking late in the meeting, so lots of these concepts have already been covered by really well and introduced by previous speakers. So there'll be, I don't have to spend too much time, so particularly by Renata and by Daniele. And I'm within this context of a gravitational theory, gravitational path integral approach to the problem of quantum gravity. What does recovering GR look like? I'll then introduce the causal set approach to quantum gravity. I know that it won't be familiar to some people in the audience, so I'm going to give a brief introduction to its basic premises, motivations, and then I'll talk about the path integral in causal set quantum gravity, which is transformed or is interpreted. It becomes a path sum rather than a path integral because causal set quantum gravity is a discrete theory. In the path sum for quantum causal sets, we need to know what S is, the action, in order to know what the weight of each configuration is. So I'll spend most of my time talking about what we know about the action of a causal set and some of its properties. And I'll give you two conjectures about this action. When the action evaluated on what I'll call manifold-like causal sets, and I'll explain what I mean by that. And then I'll do some hand waving about if these conjectures are true, what that might mean about some conditions on physical spacetimes that might emerge from such a quantum gravity theory. In particular, I'll wave my hands about some indications that this might rule out the possibility that spacetime has time-like boundaries. So here's a quotation from the Feynman lectures on physics there. It's from the volume on quantum mechanics. So he's introduced the path integral for ordinary non-relativistic quantum mechanics. And he says, suppose that for all paths, the action S is very large compared to h bar. One path contributes a certain amplitude. For a nearby path, the phase is quite different because with an enormous S, even a small change in S means a completely different phase because h bar is so tiny. So nearby paths will normally cancel their effects out in taking the sum, except for one region, and that's when a path and a nearby path all give the same phase in the first approximation, more precisely the same action within h bar, and only those paths will be the important ones. So what I'm going to do is take, and I don't think that I'm the only one here who interprets this as a heuristic argument for how classical physics is recovered from quantum physics within a Lorentzian path integral framework, because a classical path is one such that nearby paths have the same action to first order in the perturbation. So those paths, the contribution of those paths to the sum-over-histories will add up. There'll be, if you like, constructive interference between those paths and paths far away from the classical path. The contributions to the path integral from those paths will all tend to cancel out. So there'll be, if you like, destructive interference between those paths. So it's a heuristic argument. There's no framework for an interpretation of quantum physics in this path integral setting that step by step in a logical manner says that you can predict classical behavior. But to my mind, this heuristic argument is going to be part of the truth. So it's going to be part of our eventual understanding of how classical physics emerges from quantum physics. And I'm going to take this seriously as the basis for the argument that I'm going to make in quantum gravity. So Renata's already introduced this path integral for quantum gravity, and I put it in inverted commas for all sorts of reasons. One of which is that it's, as you write it down, it's purely formal, it's very heuristic, and it's what Renata calls a statement of intent. So we intend to calculate something like this, where the path integral is over geometries, little g, in some class of geometries. That's for us to decide which class. Some topological manifold M in some class of topologies for us to decide, and it could just be one single manifold. But this is our guiding heuristic in a path integral approach to the problem of quantum gravity. Now, basing quantum theory fundamentally on the sum-over-histories or path integrals is a work in progress, and I mention here Jim Hartle and Raphael Sorkin as the people who have advanced this project with quantum gravity in mind the furthest. And on their view, a sum-over-histories quantum theory is a species of measure theory. It's a generalization of stochastic process in which the primary physical concept is event and not observable. But that's, in order to explain that, I would have to give a completely different talk. So I'm not going to say any more about that. We're just going to, for the purpose of this talk, we're just going to use a rough scheme of interpretation based on the Feynman quote. And so we ask for our path integral for quantum gravity, which classes of histories dominate, which classes of histories have amplitudes which add up, and which classes of histories are suppressed. In other words, which classes of histories have amplitudes which cancel out in our sum-over-histories for gravity. So then for GR to emerge from path integral quantum gravity a la Feynman, we need suppression of a class of the class of all the bad histories. And I'm going to say something specific about what I mean by bad histories in a moment. Just for now, those are histories which have nothing to do with large, smooth, classical geometries. So we want destructive interference between these bad histories, and we want the class of histories which are close to some nice GR solution. We want the amplitudes to add up. We want those histories to dominate. So that's the rough and ready interpretation of how of this path integral, of how GR could emerge from this framework. And you could think of one aspect of the cosmological constant problem in quantum gravity within this framework, from this path integral perspective, is that bad histories threaten to dominate, in which case there'd be no continuum regime at all. So that you can see that this is connected to what one thinks of as the usual way the cosmological constant problem is that the natural value for the cosmological constant is 1. And if it's 1, then there will be curvature on Planckian scales everywhere, and there won't be any nice smooth geometry at all. So there's no continuum regime. So the two problems, so they're just different ways of this domination of bad histories is in the path integral is another way to think of the cosmological constant problem. Right. So I'm going to tell you how these questions and these issues play out in a particular approach to the problem of quantum gravity, causal set theory, founded and it was suggested and proposed independently by Jan Meerheim, by Gerarda Tuft, and by Raphael Sorkin, David Meyer, Juhan Lee, and somebody remind me of the fourth author. Well, yes, Luca Bombelli. Yes, thank you. And Raphael Sorkin has been the main champion of this approach to problem of quantum gravity since then. And it's based on 3 things. One is fundamental physical discreteness of space-time. One is order. The idea that order is a more primitive organizing principle for physics, even than space and time. So the space-time causal order, that is, if you like, the light cone structure of all continuum space-time structures, is what survives in the deep theory. And here is an example of a 5-element causal set. A causal set is a discrete order, or mathematically that's equivalent to a transitive directed acyclic graph. So it's a purely combinatorial object. And the elements of the causal set here, there are 5 of them. You can think of those as nodes of your graph or vertices of your graph. The edges denote relations. So D precedes, and it's a directed graph. So there's a direction on each edge. So each edge indicates a relation. So D precedes A precedes B, D precedes C. And the relation is transitive. So D precedes A and A precedes B means that D precedes B. But it's convenient to draw partial orders or orders as Hasse diagrams in which you omit the edges which are implied by other edges. So because you know that D precedes A and A precedes B from the diagram, you don't need to draw on this edge between D and B. It is a relation in the order, but you don't need to draw it. So this object is called, this diagram here is called a Hasse diagram of the order. You can infer all the relations just by the edges that are drawn. And these edges that are drawn they're the irreducible relations, and they're called links in our terminology. So the scale of the discreteness is proposed to be of order the Planck scale. So that means that in the observable universe, the age of the universe is 10 to the 60 Planck times. So the space-time volume of the universe is 10 to the 240 Planck volumes. And these elements of the causal set, they're atoms of space-time. So Daniele referred in his talk to atoms of space, the fundamental building blocks of space. But the elements of a causal set are the building blocks of space-time. They're atomic events, and it's space-time itself that is the whole of space-time, which is made up of these space-time atoms. So elements of the causal set are space-time atoms. And then the final ingredient is the path integral that I've already mentioned. So in causal set quantum gravity, this heuristic or statement of intent becomes or is interpreted to be, most fundamentally in the full quantum gravity theory, in the full theory, a sum over causal sets. And it's natural for reasons that I don't have time to explain, that to fix the cardinality of the causal sets that one sums over. So here's the parameter, which I call capital N. So it's a sum over causal sets of cardinality n, that is causal sets that have n elements. There are finitely many of them. You weight each causal set by e to the I, the action of that causal set, and you just add up all those complex numbers over all the causal sets of cardinality n. There may be some other weights in here, depending on how things go. You saw that in Renata's causal dynamical triangulations sum, there was a weight of 1 over the number of automorphisms of the triangulation, and we might want to put in such a weight there or not. So there are some questions. It's not doesn't have to be exactly this, but it's going to be of that form.
Space-time B plus one dimensional.
No, there's no dimension a priori for these atoms. They have no structure at all. So I'm going to show you that a causal set, not something as simple as this, but a causal set can be have an approximation which is a manifold of 2 dimensions or 3 dimensions or 4 dimensions. So there's no dimensionality to the atoms of space-time. Any site? Is that SITES site? SIZE. Oh, size. Sorry. Only in the continuum approximation. Only when the causal set has a continuum approximation, then you could associate a fundamental space-time volume which is of Planckian size. That's a useful heuristic to have, but in and of itself, they don't have a size. Yeah. No.
So the scale in the end will be some Planck length.
Yes. The scale in the end will be the Planck scale. Yeah. That's why I put this number here. So yeah. Yes, indeed. Yeah. So in this Feynmanian hand-waving interpretational scheme for the recovery of general relativity, we can already predict something from causal set quantum gravity, which is that space-time cannot have closed causal curves because there are no causal sets that are approximated by spacetimes with closed causal curves. So that whatever emerges from causal set quantum gravity, it cannot be spacetimes with closed causal curves. So that's already, you can say we put that in by hand by requiring, see here, a causal set, an order in mathematically is a transitive directed acyclic graph. So there are no cycles. You can't go around in a loop following the order. So I've ruled them out here. So that it's slightly more than just an assumption. So I can explain why. If you added the loops, you still wouldn't be able to get spacetimes with closed causal curves. But if you want to ask me that later, I'll explain why. Okay. So why causal order? Why do we choose causal order? So there's lots of different structures that a Lorentzian manifold has in GR. Why do we choose causal order to be the structure which survives in the deep theory? Well, causal order is central to GR, to the physics of GR. You just have to open a GR textbook and you find Penrose diagrams galore. And then black holes are the epitome of GR. And Steve, I think, emphasized how much that many people take black hole physics, and particularly black hole thermodynamics and black hole entropy, to be one of the important clues to guide us towards a theory of quantum gravity. And black hole uniqueness theorems, no-hair theorems, Hawking's area theorem, they all follow from the causal nature of the event horizon. So the event horizon is defined in terms of the causal structure of space-time. And in particular, the black hole uniqueness theorems depend on this causal definition of the event horizon. So, and black hole, all of black hole physics depends on the uniqueness theorems. If it was possible for, so it means that the final state of gravitational collapse is a Kerr black hole, essentially, and that allows us to do black hole physics. If you didn't know that, if there were so many different final states of gravitational collapse, then none of the physics of black holes would fly. Yeah.
Can you explain the absence of time in the Wheeler equation?
Can you ask me that later? That's not really in. Yes.
It's not really there, but I mean, it's a related question because when we talk about causal, we have to go with the coordinate time. But in quantum cosmology, coordinate time does not appear. It's only the, for example, in cosmology, only the scale time.
No, the causal structure is a coordinate independent structure. It doesn't depend on the coordinates. Yeah. And we have a theorem which I've called different things over the years, as Sumati knows. The Kronheimer, I've now come to call it the Kronheimer-Penrose-Hawking-Malamud theorem, and it's a concatenation of many different results proved over quite a long period. And so by these people. And the theorem says that the space-time causal order, in other words, all the information about which events are in the causal past and causal future of each other, so this is a continuum theorem, I should say. The space-time causal order in Lorentzian geometry gives the topology, including the dimension. So if you don't know the dimension, you need to know, if you know the causal order, you can determine the dimension. The differential structure, and almost all of the metric, but not quite. So it gives you 9/10 of the metric in 3+1 dimensions. In other words, it's only the conformal factor which is missing information. So in other words, if you know the order in the continuum, if you know the space-time order, causal order, and you know the volume measure, so you know root minus g, or another way to say it, if you know the volume of every space-time region, then you know the full geometry, the full metric, everything, manifold, topology, differential structure, metric. Then for a discrete order, in other words, a causal set, the counting measure can provide the volume. So if you want to know the volume of a particular region, you count the number of causal set elements, the number of space-time atoms in that region, and that is the volume in fundamental unit. So the slogan of causal set theory is order plus number equals geometry. And this is a theorem, a continuum theorem. This is a conjecture, right? So it's the central conjecture of causal set theory. Okay. So let me say a little bit more about what that conjecture means. So there's a discrete continuum correspondence for causal sets. So if we have a causal set, one of these discrete orders, then it recovers a manifold, a Lorentzian manifold, continuum manifold, MG, a Lorentzian geometry, if the causal set faithfully embeds in that manifold at Planck density. In other words, you can embed the elements of the causal set into the space-time such that the number that you embed in any region equals the volume in fundamental units for large physically nice regions. You don't care about the little regions, but so long as the nice physically nice regions have the right number of elements embedded in it, and the order of the causal set equals the causal order of the embedded point. So you start with your graph, which has these order relations, but when you embed the elements in the manifold, then if two elements were ordered in the causal set, then where they're embedded in the manifold has to the light cones have to match. Okay. And we can produce such causal sets by the bucket load on a computer by a Poisson process of sprinkling into the manifold. So you take your manifold and you choose points in it via a Poisson process at a particular density. And then you endow those points with the order relation that the light cone structure gives you. And I'll show you an example in a moment. And that then you take away the manifold and you're left with just the causal set, the discrete order. So I have to tell you that if you have a lot of students, undergraduate students who need projects, then you can set that, there's a lot of spacetimes that can be sprinkled into, and you can set them to sprinkle and study those sprinklings, and it's great. So I think over the last 3 years, I think I've supervised about 25 undergraduate projects like this. So it's fantastic. Okay. So what's the evidence that this correspondence holds water, that it's indeed true? So the idea is that if you have a causal set that faithfully embeds, it's faithfully embeddable into this Lorentzian manifold, then that Lorentzian manifold is a continuum approximation of that causal set. So the thinking is that the causal set's the real physical thing, the continuum manifold is the continuum that is the approximation to it. So why do we believe that this works, this holds water? Well, as I said, it's a conjecture. But we have the Kronheimer-Penrose-Malamud theorem behind us because we know that in the continuum, causal order and volume give you metric. We have causal order and number, so we're in good shape. There's a theorem that says at infinite density, so if you take this Poisson process and you keep doing it, so you build up your causal set until it's infinitely dense, then that infinitely dense causal set recovers the manifold, it just recovers everything about the manifold. Even though it's a discrete entity, it's countable, it will give you by a Dedekind completion process, it gives you back the manifold, its topology, and its metric with probability 1, because this Poisson process is a random process, so it can give you screwy things. But with probability 1, those screwy things you don't get those screwy things. And then there's direct evidence that we can read out the geometry from a sprinkled causal set. So we can do this sprinkling process, and typically what we do is we do it in Minkowski space. We sprinkle, and I'm going to show you an example. We sprinkle into Minkowski space. Forget the Minkowski space, just take the combinatorial object that you've produced and read out topological and geometrical information from it. For example, the dimension, spatial topology, and geodesic proper time. And we have both numerical evidence and analytic results that show that those things work. You can indeed, just from the combinatorial data of the causal set, recover this topological and geometrical information. Okay, so here's an example of a sprinkled causal set. So it's a causal set that by the hypothesis is well approximated by 2D Minkowski space. So the way I make this thing is I start with 2D Minkowski space and I produce this causal set, and then I forget the Minkowski space and ask, can I recover the geometric information of Minkowski space just from the graph, right? So how do I make the graph? Well, first I choose some density, and I choose a random number which has the a fixed number as the mean of the number. So I choose some number, and then I choose to put these at random places in this Minkowski case according to the area measure. So they're just randomly assigned to positions in this 2D Minkowski space. Then I draw an edge between points which are causally related to each other. Then I throw away the edges which are implied by other edges. So I take this so-called transitive reduction until what I have left is one of these Hasse diagrams. So all of the blue lines that are left are relations, but they're irreducible relations. They're links. So they're nearest neighbor relations in the graph. And you can see this illustrates the non-isotropy of Minkowski space. Minkowski space is not isotropic. It has preferred directions. Those preferred directions are the null directions, which you can see on this diagram. So this the sprinkled causal set reveals something about Lorentzian geometry that you can't see just by looking at a piece of paper, because your brain puts a Euclidean geometry on a piece of paper or on a computer screen. So the fact that this point, so I picked out 2 points here. This one pointed to this green arrow, and that one up there, that there's a link between them. They look far away in this frame, but there's actually a very short proper time between them. So they are actually close. Okay, so on Planckian scales, the hypothesis of causal set theory is this is what 2D Minkowski space looks like. And that the idea is that the deep structure of a continuum manifold and metric is a causal set. Okay. Every nice Lorentzian geometry is an approximation to some causal set, because I can take that geometry, I can do this sprinkling process, produce a faithfully embedded causal set from it. And the idea again is that the causal set, which is made of these space-time atoms, this discrete combinatorial object, corresponds to an approximation, which is like the fluid approximation as Daniele was mentioning, but this is a space-time fluid rather than a spatial fluid. So the space-time fluid is made of these fundamental discrete space-time atoms, but the fluid-like approximation, the continuum approximation, is a Lorentzian geometry, continuum Lorentzian geometry. And here's our interpretation now, or our understanding of the gravitational path integral as a path sum over causal sets. And so this sum, if n is large enough, let's say 10 to the 240, then within that class of causal sets, there will be, so the sum over all causal sets of that cardinality will include all nice Lorentzian geometries, and in fact many times, because this Poisson process can produce lots of different causal sets when you run it again and again and again for the same space-time, you get different causal sets, but they're all approximated by the same geometry. So this sum includes causal sets which are approximated by nice Lorentzian geometries. By nice, I mean that they don't have curvature on Planckian scales. So they have to be smooth enough. Otherwise, it doesn't make sense for them to be approximated by a Planck scale discrete object. Just as it wouldn't make sense to have a fluid such that the density of the fluid is changing over intermolecular scales. That wouldn't make sense. That's just a violation of the idea of fluid approximation. Okay. And it includes all nice topologies, including all dimensions. So this is the answer to your question. So I can create a causal set from a space-time with 3 dimensions or 2 dimensions or 5 dimensions or 4 dimensions. And if it's of cardinality 240, it will be included in this sum. And it includes a lot more. So most causal sets of cardinality n are not like manifolds at all. And when I say most, I really mean most. So by a long way. And I'm going to come back to that in a moment. So to complete our theory, one of the things that we need is the action. So what's the weight of each causal set? So we need this action S of a causal set. And we have some candidates. And in fact, there's a one parameter family of candidates where the parameter is associated, it's going to be associated to dimension. But for now, it's just an integer, a natural number, a parameter. I'm going to give you two examples of this family, one for 2 dimensions and one for 4 dimensions, but there's a similar action for every dimension. So yeah, so there's one parameter family. So C is a finite causal set, and the 2-dimensional action is this object. So n is the cardinality of the causal set. N1 is the number of links. N2 is the number of 3 chains, and N3 is the number of order intervals of cardinality 4. I have to explain what that means. But so here's a causal set. Like that. Well, maybe that's too complicated. I don't want to give myself too much work. All right. So this is the Hasse diagram of a causal set. So of course this one is related to that one, but we don't draw a relation, an edge between here and here directly because we don't need to. So n is 1, 2, 3, 4, 5, 6, 7. So n equals 7. N1, that's the number of order intervals with cardinality 2. So an order interval is a pair of elements which are related, and all of the elements that are causally between them. So an order interval of cardinality 2 is a pair of elements, and you've exhausted the cardinality. If you take that pair, you've already got 2, so you can have nothing in between them. So it's every link. So in fact, it's every edge in the Hasse diagram. So it's 1, 2, 3, 4, 5, 6. Oh, it's 7 as well. Okay. All right, N1, that's N1. N2 is the number of order intervals of cardinality 3. That's pairs of elements which have exactly one element between them, right? So I look at all pairs of elements and I decide whether they have one element between them. And if they do, I count them. So if I take this pair, for example, that's not an order interval of cardinality 3 because there are 2 elements causally between them. So I don't count that one. But this one and this one, that has cardinality 3, and this one has cardinality 3. So that is 2 of them, I think. Oh, there's that one. Yes, I'm sorry. Yes, that one is also, yeah. Top right. Oh, that one. Yes. Sorry. Okay, good. 4. Okay, thank you. And N3, that's order intervals of cardinality 2, and there's 2 of those. There's this one, the diamond, and then there's this one. Right, that's called a 4 chain. Right, so there's 2 of those. Right. Yes, thank you. Yeah, fast learners. The pupils are they're passing the pizza. Okay. Right. So then you add them together with those numbers, whatever they are, and you get a number for the action. Right. So and then the 4-dimensional action is similar. You have now instead of 2 out here, you actually have a dimensionless number of order 1, and you add another number to this sum. So n4 is the number of order intervals of cardinality 5. Right, so that would have n4 would be 0 in this case. So there's no order intervals of cardinality 5. But one nice thing about this is about the actions, apart from how simple they are, is that they very much follow the same pattern that Renata showed you for the Regge action. So these are numbers, they're combinatorial things, you're counting things. But what you're counting in this case is not simplices, subsimplices of your simplicial complex, but these numbers of order intervals. So they're very non-local things. They're not nice local things like simplices. They're very non-local things. They can stretch across the whole causal set. So, and this number, and this is a theme which Daniele and Renata both had in their talks also. This number doesn't really have any interpretation as such in the fundamental theory. Eventually, it's going to be related to the ratio of the fundamental length, which is 1, right? So it's a fundamental theory. There are no free parameters. There's there's nothing except 1. So this is and the Planck length, the actual Planck length. So the number which is 10 to the minus 33 of order 10 to the minus 33 centimeters. So eventually, when we have our full physical theory, it's going to be related to that. But in the
The sign, like plus minus.
Yes.
Like minus for even cardinality and plus for odd cardinality. Is that what happens?
I think so. That may be a pattern that holds for all of the different dimensions. But yeah, I'll have to check. But yeah, I think so. But yeah, so these alternating signs are absolutely crucial. They're going to play an important role. Okay, so for either this, or any of the family of actions, you can take any causal set at all, any causal set you like, plug it in, and you'll get a number. So they are causal set functions, functionals, right? You plug in a causal set, it spits out a number. There are special causal sets that we're particularly interested in, and those are the sprinklings. Those are the results of this Poisson process, the ones that faithfully embed into manifolds, the manifold-like causal sets. And if you sprinkle into some d-dimensional spacetime at some density, and that density, this thing is L. So the density rho of the Poisson process is a length to the minus d in d dimensions. That sprinkling process turns these causal sets into random variables because you have your manifold, fix that, right? So for any manifold, it gives you a random variable. So fix your Lorentz manifold, sprinkle, gives you a causal set, a random causal set. Plug that random causal set into this action, and you get a random number. So the sprinkling process, which is fixed to a particular space-time manifold, turns any one of these causal set actions into a random variable, which is tied to that manifold. Right? So you can ask, how is that random variable, which is one of these actions with in d prime, where the parameter is d prime. So d prime would either be 2 or 4 or whatever you choose. How is that random variable related to the Einstein-Hilbert action of this manifold that you've created the sprinklings from? Right, that's a question I'm going to come back to. Okay, so let's look at the behavior of these causal set actions. This action has to be super special if we're going to get GR back from our causal set sum, because it must suppress the bad histories. And the bad histories in a causal set sum-over-histories, they're very bad, and there are a lot of them. And we know exactly how many there are. So the number of causal sets of cardinality n grows like 2 to the n squared on 4. So it's super exponential growth of the number of configurations in your sum-over-histories. And the vast majority of these are the so-called Kleitman-Rothschild orders. And they are these weird things. I mean, we kind of love them and hate them, but so a Kleitman-Rothschild order of cardinality n is a 3-layer thing. And the layers are, you have roughly n over 4 elements in the bottom layer. You have roughly n over 2 elements in the middle layer, and the remaining n over 4 will be in the top layer. And then each of these elements is below roughly half of those. So you can generate Kleitman-Rothschild orders by a random process. You just put this below, make a link between this and this with probability of half. So you just get a whole bunch. So it'll be this, 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 this one, the same, this, 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 this. So that's how you make. And similarly for these ones, these will be above roughly half of the middle ones. That's the KR order. And it's nothing like a manifold. It's not manifold-like in any way. And the number of these grows like 2 to the n squared on 4. So if you have a big bag of n of causal sets of cardinality n, where n is a very large number, you put your hand in and you draw one out uniformly at random, you'll get one of these. It will be a KR order, overwhelmingly likely to be one of these horrible. Yeah, we love and hate them. So that's a huge entropic weight in the sum over histories. Just vastly most of them are these non-manifold-like causal sets, and we don't want them in order to get GR out. We need them to be suppressed, and the thing that's going to do the suppression is the action. So the action of a KR. So the action. Let me go back to the action. So apart from this cardinality term, these terms go like the number of relations, the number of links, the number, and that number goes like n squared. And for KR orders, there's no cancellation between, you've got these alternating signs, but for KR orders, there's no real cancellation between these terms. They're massive, they're of order n squared, and they just add up, and the action is of order n squared. The typical size of this causal set action shows that it's non-local. So a local action would grow like n. So n squared shows that it's non-local. In fact, it shows it's bilocal. So it's showing this bilocal nature of the causal set action. And therein lies the hope that the action can counter the super exponential entropic weight of the KR orders. And remarkably, and Surya is going to give a talk on this next week, but since she's people who are not here next week, Sumati is here, so we can get her to give us a preview of her talk. You can show that if you take the sum e to the is, where s is one of these, any one of the causal set actions I've shown you, and you sum it over the causal set, over the set of KR orders, then in the limit of I put rho goes to infinity, it should be n, so n goes to infinity here. N goes to infinity, it gives you 0. And the limit is it's approached exponentially fast as n increases. So for any choice, and this is for any choice of the action, but there has to be a bound on the dimensionless number multiplying the action. So here's this dimensionless number. It can't be anything, but there's just some bound on what it can be, which is the bound is of order 1. K-layer orders are also suppressed for any fixed K. So the KR order is a 3-level order, but you can have a 5-level order and rule those out as well by the same kinds of techniques that Sumati and her collaborators are using. And so a very large class of bad histories, in fact, the most numerous ones in our big bag of all causal sets, are suppressed in the sum over histories. Okay. So what about the other side of what we need? We need bad histories to be suppressed, but we need good histories, in other words, the manifold-like ones, to be enhanced. How's that going to work? Well, if your causal set action the dimension of that doesn't match the dimension of the manifold that you made your causal set faithfully embeds into, then there's no relation between this random variable and the Einstein-Hilbert action of the manifold. And a typical value of such a of the action for such a sprinkling is again non-local. It's n squared, so it's huge, right? So if your action and if you put a 4D action, so you choose 4D for your action here. If you evaluate that action on a causal set which is 5-dimensional, you'll get something of order n squared, something huge. But if you evaluate it on the right, a manifold with the right, on a spacetime with the right dimension, in other words, one that matches the action, then we have a conjecture. So if D is equal to D prime, then we have a conjecture. If the manifold that you've sprinkled into is globally hyperbolic, then as the density of the sprinkling tends to infinity, then the mean over sprinkling, remember this is a random, thank you. Is that 10 for me speaking or 10 for the whole? Okay, cool. Let me see. Okay, I have 3 slides left, so hopefully, okay. So the mean over this Poisson process of the action is the Einstein-Hilbert action plus a term which we have been calling the joint term. And the joint term is it's an integral over the intersection of the past and future boundaries. So for a globally hyperbolic finite volume space-time, here's the classic example of such an object. This is globally hyperbolic. It's the causal interval, and the joint is this. So the future boundary is this, the past boundary is this, and where they intersect is the joint. So this is J. And what you do, let me specialize to a particular case, which is exactly the causal interval. There, this funny hyperbolic cotangent just becomes 1. So in fact, this is just the area of the joint. Okay. So that's our conjecture. And what the work that I've been doing with my undergraduate students at the moment is that we, for more general regions of space-time, for example, if I take a flattened cone, so these boundaries are now space-like and not null, then this joint term is not the area, but it's an integral of this hyperbolic cotangent of the Lorentzian angle between the two space-time, the two space-like surfaces where they meet. I'm going to skip over this. So, okay, we have evidence for this conjecture. It's not a theorem, but it's a conjecture. But we have evidence and lots of different examples by now. Okay, so student projects are just showing this for more examples. Okay, I promised you timelike boundaries, so I feel I should, so forget this little bit up here. We have another conjecture, which is that if you have a manifold which has a timelike boundary, so classic example would just be a square in 2 dimensions, right? That's not globally hyperbolic, has 2 timelike boundaries there. Then the limit as the sprinkling density goes to 0 multiplied by the discreteness length, which remember is, so the density is going to infinity, the discreteness length is going to 0. So the mean of the action multiplied by this discreteness length is equal to the area, the codimension 1 area of the timelike boundary. So in the 2D case, it's just the length of the timelike boundary. And this is some dimension dependent constant of order 1. And we have numerical evidence for this now. But what it means is that if you just have a timelike boundary, the action is going like the order of 1 over the discreteness length. The discreteness length is going to 0 in the limit. So this is blowing up. the action blows up and it dominates the action. So it dominates over any Einstein-Hilbert term. So you don't get anything like the Einstein-Hilbert term. Okay, so here are my speculations. So here's a question. Why do we not get boundaries into space-time? Why, when we open the door and go out, do we not just disappear off into nothing, right? Why is there no boundary there when a piece of Minkowski space with a timelike boundary is a perfectly good solution of the vacuum Einstein equation, right? So it's a solution. Why aren't there just boundaries everywhere? Well, suppose we take the action for d equals 4 and consider our sum over causal sets, sum over histories. Suppose that all the non-manifold-like causal sets are suppressed, a la this is work that somebody done with Steve Carlip, and Steve originally worked with his student. Do you know Loomis's first name? Somebody? No, I can't remember. And all those with dimension not equal to 4, which have actions which are non-local and huge, let's suppose that they're all suppressed. Then the only causal sets that we have left are ones which are 4-dimensional. Now, the actions of causal sets with time-like boundaries will be much bigger than those without. They'll be of order n squared rather than n. Small changes in a causal set with time-like boundary will result in relatively big changes in the action, and a Feynmanian cancellation will occur. So the causal sets with time-like boundaries will be suppressed in the sum over histories relative to the causal sets without time-like boundaries. And for those causal sets, the action is close to the Einstein-Hilbert action, and a stationary phase argument a la Feynman results in the suppression of non-solutions compared to solutions. So as I said, I promised you hand waving. I gave you hand waving. Okay, and I won't go over these additional points, but end here. Thanks for listening.
Thank you very much, Fay. Okay, we still have 4 or 5 minutes for questions. Let's go and then Thomas.
Does it give a signature, legal signature reactions?
That's a good question. There is a notion of horizon, which is that of causal horizon. It probably only makes sense in the context of a causal set which is infinite into the future. So in this context, where I was just looking at finite causal sets, probably isn't relevant. But the idea of a causal horizon, it's the boundary of the causal past of a future infinite time-like curve. So that includes black hole horizon. So this is a concept due to Gary Gibbons. So it includes black hole event horizons. It includes Rindler horizons, because the time-like curve is a constantly accelerated observer, world line of a constantly accelerated, and it includes cosmological horizons like de Sitter horizons. So it's a very general concept. So do we have a concept of time-like curve in a causal set? Well, we do, and that concept is that of a chain. So if you just take a totally ordered subset of the causal set, that's like a time-like curve. And if we have an infinite causal set, one in which it makes sense to have a future infinite chain, future infinite curve, then we can look at the causal past of that. And that will divide the causal set into 2 pieces, right? That will be the causal past and the rest. And that partition is a horizon for us. So there is a notion of horizon that, because it's all, and it's sort of natural that you have such a thing because horizons are defined in causal terms in the continuum. So we just follow our nodes and do the same thing in the causal set. What that has to do with this and the action of such an object, yes, I don't know. All of this is in the context of finite causal sets. Those numbers are all just, they're just numbers, finite integers. So I don't know. That's a good question.
It was Thomas, then Renate, and then Neil.
Yeah, maybe it's too much out of context, but so in the context of Carlip theory, which at least relativity with say very light matter. There's like Witten's bubble of nothing, and that seems to be a case, which is something with a timelike boundary, which is believed it's a very physical solution. So I'm wondering to what extent it contradicts this. I know it's not about causal set theory, but nonetheless, it's considered to be a healthy solution of relativity. And it has a timelike boundary.
Does it though? I mean, isn't it? I mean, isn't it just infinite, spatially infinite? Is there really a timelike boundary?
Space would be like a general bubble. If you go in, there's nothing.
Oh, but that's not. There's no boundary. I mean, there's no boundary there in space. I mean, there's no edge, right? It's a bubble of nothing, but it's like there's nothing inside a donut, but there's no edge to the donut, right? Yeah, there is no right. So yeah, it's a bubble of nothing, but there's no edge to space, right? Like a donut has a hole, but so you'd say there's a hole, but but it's only in the only.
A wall that I can approach and I can move towards it.
Oh, you mean in the 4D picture? Okay, so because the fifth dimension degenerates.
Right. In fact,
right.
It's not, but
okay.
It does look like exactly a solution.
Okay. I understand. Okay. Yeah. So I think that the 5-dimensional. I mean, it makes sense as a manifold without boundary in 5 dimensions. So it would be perfectly okay. So yeah. Sorry, I misunderstood your question.
Renata?
Yeah. Also, I mean, I find that the timelike boundary. I find it fascinating. And you started out by saying, these are certain questions, I expect quantumgravity will address for me. And I thought they were kind of, related to local HBAR things. Okay, we have a wormhole, they're possible classically as well. But maybe the quantum wiggle will allow it. So there one would say, okay, then the gravitational quantum theory goes genuinely beyond what GR is, right? But here you're giving us something which is very surprising. That you're excluding stuff that seems perfectly fine from the point of view of GR, by some argument that comes out of your formulation. So, but first, I find this very striking, and I think, okay, can that really be true? I mean, where is the H-bar effect? And then you're saying, okay, there's some cancellation effect in the path integral, and that will of course be based on really, some exact cancellation around something that's a classical solution. So, back to finite intuition, taking very seriously classical solution, and then has a kind of cancel paralyzed. Should I really believe such an argument? Where's the H-bar flavor?
Yeah. I think there's no H. I mean, in the sense that it's just a non-perturbative effect. It's not an H-bar effect. It's not something that you would see in a perturbative expansion. It's the full path integral which is producing this result. So, or it would be. I'm not claiming this as a proof or any such thing, right? Yeah.
Oh, this is just some number, and it's just like people like myself. I think that's not the correct comparison. We have a certain lattice expression, and of course, it comes from a well-defined actual.
Yes.
It's not just a number. Whereas in your case, indeed, it seems much more like a number, and therefore
the action is that. Yeah.
Yes, in my formalism, it's so meaningful. So it goes beyond. Saying it's a far-reaching, maybe this aspect, generalization, or the simple discretization, like
I think you're right. I think that's a good way to put it. So it's it has more of the flavor of something that stands on its own without knowing in advance. Of course, we do both things. We start with what we know, and we try to do quantum GR, right? But we also, at the same time, well, some of us, at the same time, conjecture about what the fundamental degrees of freedom are, if one wants to say that, and say that you can't deduce that from what we know. I mean, if we could deduce that from what we know, then somehow it wouldn't be novel physics. So I'm taking the Donahue fork in the road, right? The Donahue fork in the road is, do we take the degrees of freedom that we know from the physics that that we trust, and we add new interactions, we laticize it and try to follow the prescriptions of calculating the path integral from that we have done with other theories, and let that lead us to the full theory, right? We try and do that. So that's one approach. The other approach is to say it's the the QCD option, the QCD fork in the road, which is to say, well, your the four Fermi theory using pion degrees of freedom, you can't fix that. You have to postulate new degrees of freedom for the theory, for the deeper theory. So that it's the latter. So choosing the latter option. So, and then of course the action doesn't look like, the action in that deeper theory with new degrees of freedom, these discrete order relations. So those are the degrees of freedom. It can't look like what we know. It can't be familiar to us because it's a new thing, right? So and it doesn't. Yeah, you don't see Einstein-Hilbert in that at all. But the claim is that it does come out for particular causal sets. So this is our conjecture for particular causal sets. When you have a very high density sprinkling into a manifold, and you take that causal set, then the action is approximately the Einstein-Hilbert action. I don't know what to think about this joint term. I need to discuss that with people. Renormalization, well, I value the input contributions and thoughts of all the experts here because it's something that, I don't know how to approach, but yeah. But you're right. I agree with you.
Okay. Neil, if it's okay for you, we start with your question after the coffee break because we are quite late. Okay, thank you. So we will meet again at 11:45 and let's thank Fay again.